here is a problem where the applied field strength and as well as the gyromagnetic constant for a particular nucleus has been given, and we have been asked to determine the frequency and the energy in joules per mole that it requires for it to flip from the alpha spin state to the beta spin state in an NMR experiment. Okay, so let's write down first all the different formula that we might be needing for this problem. So first, to begin with, a very famous energy and frequency relationship, which is delta E equals h nu. And we already know that this nu is nothing but the frequency, right? So this nu can also be written as nu equals gyromagnetic ratio divided by 2 pi times magnetic field strength. Okay, and apart from that, we also needed to know the value for Planck's constant, which is going to be equal to 6.626 times 10 to the power of minus 34 kilogram meter square by second. Okay, but we can also convert this into joule second. Say, for example, joule, the relationship between joules and kilogram is going to go like this. 1 joule is going to be equivalent to 1 kilogram meter square by second square. If you multiply by seconds on both sides, you will be getting joule second equals kilogram meter square by second. And in place of this, you can put joule second. Okay, so we are going to rewrite our units for Planck's constant so that it will be much easier for us to work when we convert it into like the final unit that we want. Okay, so 10 to the power of minus 34 joules second. Now that we have all the formula and units, let's work on the frequency for the hydrogen nucleus. Okay, so for hydrogen nucleus, the frequency is gyromagnetic ratio times B0 divided by 2 pi. The gyromagnetic ratio for the hydrogen nucleus is 2.67 times 10 to the power of 8 Tesla raised to the power of minus 1 and S raised to the power of minus 1. Okay, so make sure that you put all the units in place. So it's going to be 2.67 times 10 to the power of 8 Tesla raised to the power of minus 1, S raised to the power of minus 1. This has to be multiplied by B0. My B0 for the hydrogen nucleus is actually 7.05 Tesla. Okay, so this is the magnetic field strength present in the NMR instrument. Okay, divided by 2 pi. Now we can cancel the like units. Okay, Tesla raised to the power of minus 1 and Tesla will get cancelled. And the final number for this is going to be like this. When you multiply 2.6 times 7 times 7.05, it's going to be 2.997 times 10 to the power of 8 S raised to the power of minus 1. And I've also divided by 2 pi. So everything put together, this is the final number that I'm getting. But remember, we are talking about the frequency. The frequency can have different units, right? It can be cycles per second or it can be hertz. But you can, if you want, you can convert this into hertz. If we convert this into hertz, we know that 1 hertz is nothing but 1 cycles per second, right? So you can just convert, keep this as hertz, right? So 7 times 10 to the power of 8 hertz. And we can also convert this into megahertz since the number is like really large. So that's going to be equivalent to 2.997 times 10 to the power of 8 hertz. 1 megahertz equals 10 to the power of 6 hertz. So the hertz and hertz will get cancelled and you will have your final number, which is going to be equivalent to 2.997 times 10 to the power of 2 megahertz. Remember, this 10 to the power 6 and 10 to the power 8 will also get cancelled and you'll be left with 10 to the power of 2. Okay, when you multiply, it's going to be 299.7 megahertz, which can be equivalent to 300 megahertz. This is going to be our frequency for the hydrogen nucleus. Now let's calculate the energy for the hydrogen nucleus for it to flip from alpha spin state to the beta spin state. Okay, now again, our formula is going to be delta E equals h nu. Now let's apply the value for Planck's constant with joules and seconds as units. Okay, so the value for this is going to be 6.626 times 10 to the power of minus 34 joules second. And we have already calculated the frequency here. This is in 300 megahertz. So again, like this is where we need to be like really careful. We have to convert this into seconds again, right? So it would be making much sense if you would have left it here at this point, so the seconds and seconds can get cancelled later on. Okay, but it's completely fine. We'll just keep it as 300 megahertz, and 6.626 times 10 to the power of minus 34 times 300 megahertz is nothing but 300 times 10 to the power of 6 hertz. And I don't want to keep that as hertz. Instead, I want to keep that as seconds. So I'm going to replace it by 1 by second. Okay, and this second will get cancelled, and the final number is going to look like this. When I multiply 6.626 and with by 300, it's going to be 1987.8 times 10 to the power of minus 28. Okay, with also taking into consideration 10 to the power of minus 34, the difference between 10 to the power of minus 34 and 10 to the power of 6. Okay, so this is in joules. This answer is in joules, but looking at the question, they wanted the answer in joules per mole. For that, we have to divide it by mole. So 1 joule, the joule per mole is going to be calculated by 1 divided by 6.022 times 10 to the power of 23 particles. So this is going to be a Avogadro number. Say, for example, if you want to convert moles to number of items or number of particles, then it should be the Avogadro number. So that value is going to be equal to 1.66054 times 10 to the power of minus 24. Okay, and since we want to convert this into joules per mole, we are going to divide by this number because it's per mole. Okay, so that's going to be equal to 1987.8 times 10 to the power of minus 28 divided by 1.66054 times 10 to the power of minus 24. And this is in joules per mole, right? And when this 24 goes to the top, it's going to be plus 24, right? So therefore, it is going to be on the whole, it's going to be 10 to the power of minus 4. So I'm hoping that you can do the math. So on the whole, it's going to be 1197.0 times 10 to the power of minus 4 joules per mole. That is also equivalent to 0.119 joules per mole. This is going to be our final answer for the hydrogen atom, for the amount of energy that the hydrogen atom needs in order to flip from the alpha spin state to the beta spin state. Let's do the same thing for the carbon. Okay, so all you have to do here is we needed to find the frequency for which only the gyromagnetic ratio should be changed. Okay, so let me set up the equation. So that's going to be for carbon 13. And the gyromagnetic ratio here is going to be 6.688 times 10 to the power of 8 Tesla raised to the power of minus 1, S raised to the power of minus 1. And the magnetic field has been kept constant here. So same thing. There has been no change except for the gyromagnetic ratio because the nucleus is different here. And then when you do all the math here, it's going to be 7.50 times 10 to the power of 8 megahertz, or 8 hertz, which should be converted into megahertz. That's going to be equivalent to 75 megahertz. Okay, now that you have calculated the frequency, you can also calculate the delta E for the carbon nucleus. So delta E equals, again, we'll be making use of the Planck's constant. So 6 times 10 to the power of minus 34 joules second times 75 megahertz. So when you do all of these calculations at the end, it's going to be ending with 299.27 times 10 to the power of minus 3 joules per mole. Make sure that you do not skip any steps. It has to be going through all of these steps, okay? And then finally, it's going to be 0.029 joules per mole. So this is the amount of energy that the carbon nucleus will need in order for it to flip from the alpha spin state to the beta spin state.